So hey everyone, welcome to the Algorand Hack Reach workshop. Today we're joined by Jay McCarthy from Reach, and he'll be giving a kind of refresher session on how to use Reach for building your Algorand apps in the Algorand Hackathon. So yeah, be sure to kind of listen along, have a go of Reach. It's definitely a very easy language to deploy with, and gives you a lot of optionality. So if you have any questions, feel free to put them in the chat. And this event is being recorded, so if you miss it or want to go over something, then you can do that probably tomorrow. But over to you, Jay.
Hey, howdy everyone. So, as was mentioned, I'll talk a little bit about getting started with Reach. And to get started, first you want to go to docs.reach.sh. I've posted that in the chat, and that link will be included, wherever you found this, I'm sure. And the documentation, let me just kind of explain a little bit about what you're looking at. The overview, which you can get to through these links, kind of explains the ideas behind Reach. If you have only a few minutes to read about Reach, you want to check that out. The tutorial is like a much longer directed series of steps to make a really simple application. And, it takes a few hours to go through. The guide is kind of like answer some common questions and design issues with Reach. The workshop is sort of like suggested projects to work on. And then the reference is like, this is like the hardcore documentation that explains how every single function works. We're going to be sort of spending our time in the tutorial right now, but I wanted to let you know what those other things were. Now, what Reach is a development platform for writing decentralized applications that works really well with Algorand. So when you write a Reach program, you don't have to think about the details of exactly what smart contract you're going to write, how that smart contract works. Instead, you can focus on the business logic of the program that you're running, and you get to write in a language that is basically JavaScript, and you get to interact with your dApp using JavaScript or other languages. I'll be demoing it with JavaScript. Now, to install Reach, you're going to download something from our site. So from the documentation site, there's a file called Reach. So if we can just copy this right here. We require, by the way, that you have make Docker and Docker Compose installed. And if you're on like OS 10 or Linux, you already have this. Probably, you may not have Docker, but you probably have the other things. And if you're on Windows, like I'm on Windows, then you'll want to use WSL. If you look on this guide right here, consult the guide to using Reach on Windows, it'll walk through how to install WSL and get it all set up. Okay, so anyways, if we copy this right here, what this is going to do, I'm going to go over into my terminal, and I have a directory. Let me just blow it away real fast, called Reach in my home directory. And what this does is it downloads the Reach script. Reach is this command. Look at that. There's nothing there. We can say help. And this is how you like interact with Reach. It downloads instantly because it's really, really small. But behind the scenes, there is a whole bunch of Docker images behind the scenes. So we can call, I'm going to do upgrade and update. And what update is going to do is it's going to go and download all of the Docker images for Reach. Looks like I didn't have the latest version, so it's actually downloading a few things. And it downloads the Reach compiler, and it also downloads devnets for all of the networks that we support. So we support Algorand, Ethereum, and Conflux. But today I'll just be talking about how to use it with Algorand. Since I have a lot of the things already cached, my download is not going to take as long as yours. Your download will take quite a while because some of the images for the devnets are pretty big. Because Reach attempts to be a complete development platform, you don't need to have any other software installed. You just have Docker and Reach, and they'll get everything else that you need. All right, so now that we've got it all ready to go, we can write our first program. We can know that it's working, by the way, by writing Reach compile. And we'll see the compiler will run, and there we go. We got it running. We're using this particular version. All right. Now, if you read the tutorial, it'll step-by-step walk through how to write a simple reach program, but I'm actually going to run the reach init command. Actually, I'll create a directory called tutorial first, and I'll run reach init. And what reach init does is it creates sort of like some really simple programs that are going to be useful to get started with. It creates the programs that are walked through in the tutorial. And you'll notice, by the way, that I'm using NeoVim because I do all my development at the command line. But we actually also have a VS Code extension that works pretty well that you can install. If you like VS Code, then there's a link down here. So get language support for Reach in your editor. So you can click over here, you can look at the Reach IDE, and you can install this right here. All right. Now, I just want to walk through real fast this basic Reach program. This, by the way, is the entire sample program that you can see on my screen right now. By the way, is the program size, like, is the text size big enough? Would people like it a little bit larger? Maybe I'll just make it larger. So, oh no, that's not what I want. Okay, there we go. Let's do this. Okay, there we go. Okay, so on the top screen, we have our Reach program, and on the bottom screen, we have our JavaScript front end. These two programs work intimately together because when you write a Reach program, you are defining the code that runs on the consensus network, like Algorand, and you're also programming the code that will actually run on the individuals that are, using your dApp. In this case, we're not going to be writing an interactive program. We're going to be writing like an automated test suite that will just like test out our program to make sure things are working. So when you write Reach, you're writing in JavaScript. And so we're going to define an export called main, which is a Reach application. And then what the Reach application does goes inside of this code right here. And one of the fundamental concepts of Reach is the concept of a participant. So our participant is like the players in a game. So for example, suppose that George and I were going to go play chess together. Then we might describe that as saying, Jay and George play chess. But now when we play chess, there are two roles to fill in a chess game. There's the white player and the black player. It's relevant what player you are because depending on what player you are, you can control different pieces on the board, and also white always goes first. I think that's right. Maybe black always goes first. One of them always goes first. I'm not actually a chess player, so I don't really know. So anyways, so we could say Jay and George play chess, where Jay is the white player and George is the black player. Well, Reach works just the same way, except that we call those roles in the game a participant. So in this case, we're writing a simple program where there are two participants that we call Alice and Bob, and they don't actually do anything. And we deploy the program, and then the program will actually go here. So that's the basic structure of a Reach program. And now let's look at the front-end program, the test suite. The test suite is going to load our standard library. It's going to get the ability to load the standard library. It's going to load a compiled version of this program. So this program is called index.rsh. And when we compile it, let me just go down here real fast and compile it. Right, Reach compile. And what Reach compile does is it produces that file right there in the build directory. Okay, so we're going to import the build file, and then we're going to actually load the standard library. And then once we do that, we're going to set up completely fake test accounts. So we're going to have a fake test account called Alice and a fake test account called Bob. So these test accounts are like the actual people. So for instance, when I talked about Jay and George playing chess, this right here is like Jay, and this right here is like George. Because on consensus networks, we have the concept of the human or the principal who controls an account, and an account participates in a dApp as some role. And so these two things right here, they are the accounts, which are the principals. Now, we're all familiar with the idea that on consensus networks, one of the things that you need to do is deploy your contract. And so Reach takes care of that. We can write alice.deploy. Now, what is it that she's deploying? She wants to deploy this program. And this program came out of the compiler. So that's why we use the backend. So we imported the compiled version of the program as the name backend. And so that's what we want to deploy. We want to deploy that backend. Now, when you deploy a backend, it will actually be launched on the network. So for instance, on Algorand, it'll be launched as, application number 7022. And now we need Bob to say, okay, well, my job isn't to launch that contract. Instead, it is to attach to one that already exists. So this contract Alice get info function, that's going to return 7022. And then we're going to have Bob attached to it. Now, each of them, Alice and Bob, have a representation of the contract. With that representation of the contract, they can now actually carry out the role of the game by either acting as Alice or acting as Bob. And we do that right here by saying backend.alice, contract Alice, and backend.bob, contract Bob. And these backend functions, they return promises. In JavaScript, a promise is a value that is not yet determined, that will be determined in the future. And we can write the function await promise all to wait until all of these promises are fulfilled. So essentially that means that they are all ready to go. Now I'm actually going to change this hello right here to goodbye. And we'll go up here and we'll write hello. So hello will run before we actually interact with the contract, and then goodbye will run afterwards. So if we go down and run this program, we can write reach run, and we'll write, let me just configure it real fast so that we're going to use Algorand. I'm going to write export reach connector mode equals algo. So that is a signal that we always want to use Algorand, and I'll write reach run. Oops, reach run. And what this is going to do is it's going to take my compiled program, turn it into a Docker image, launch that Docker image, connect it to an Algorand devnet, and it runs off and goes and builds the program. Now, that actually just launched our contract on an Algorand devnet, printed hello, and then printed goodbye. If you want to see lots of output, because you find that exciting, then we can turn on debugging mode. And then what this will do is it'll give us lots more information about what's going on. So from this, we can see, for instance, that the application ID was number 9, and it was created in round 9. And we can go and we can actually look at the details of the Algorand transactions that got generated. It basically is never interesting. Well, it's never important to know these debug messages, but sometimes people want to know what's happening, even if they don't understand what it is. And it's just fun to see things go by. So maybe you would enjoy turning on debugging mode. We're not going to do that though. All right. I'm going to pause real fast because someone's asking a question. So someone asked the question, how was Reach built and what new features are coming? I think that we'll kind of reserve the question about what new features are coming for later. But if you're interested in the question of how was it built, in the guide, we have something that says, how does Reach work? And it will talk a little bit about how Reach works. And Reach is a compiler for its own special language combined with a verifier. And it's implemented in Haskell, and it uses a Z3 theorem prover for verification. If you have questions about specific things about how Reach works, I would be happy to talk about them. Everything about Reach is publicly available to learn about on our GitHub repository. So if you look at GitHub, you can see all the code and all sorts of information about how it works. Yeah, as I talk more about what Reach does now, then in the future, I can talk about what's new. Someone else asked the question, do you mean a local DevNet sandbox running in local Docker instance set up by Reach as part of Reach Init? Yep, so when we ran Reach Run, that you can see it at the very last step. See right there where it says starting tutorial DevNet algo PG and DevNet tutorial tutorial DevNet algo 1. So those right there are actually starting an indexer database for Algorand and then an Algorand DevNet. So behind the scenes, it completely creates a completely fresh DevNet that has never been used before and will never be used again. It is, when I say the DevNet, I am not talking about the beta net or the test net, the officially supported ones. These are just completely local instances that are Dockerized. Someone says, can you go into more details about the deployment part in the Algorand network? Sure, yeah. So in our Reach program, we write deploy to separate the part of our program that specifies the roles in the program from the actual steps of the program, which, by the way, we haven't written any program yet. We'll do that later. And then in our front end, we write alice.deploy. And what alice.deploy does is it will take the teal code that we generated for this program, and it will create a new application for that and initialize it with an escrow account and save the information about it. So for instance, you can, if you want to, you can see the actual code that gets generated. And we can see that, like, here is the approval program. So we actually, spit out the teal program that gets generated, and it has all sorts of things that it checks. We also have an escrow program and things like that. And so those things right there are the things that are actually launched. We completely insulate you from the need to actually ever interact with the Algorand SDK. One of the things that you'll find if you use Reach, then you will never need to import another library other than the standard library, and you will be able to interact with Algorand as well. Just as an aside, it's configured right now to use Algorand, but if we temporarily set Reach connector mode to something like ETH, then it will use Ethereum and the program runs exactly the same way. So here it's starting an Ethereum DevNet, and then it goes off and runs it. And Ethereum and Algorand are equally fast now because Reach uses the experimental Algorand dev mode, which does instantaneous transaction processing. Someone asked the question, how has Reach been adapted for the AVM? I'm sorry, I can't completely parse this question. When Reach compiles, it compiles your program to teal, i.e. the new AVM. Right now we're on teal version 4/AVM 0.9, and Reach targets the latest versions, and we work intimately with the Algorand team to make sure that we're in sync. Well, I want to sort of push forward a little bit with this program, because I've only so far told you about kind of like the structure of a Reach program. We haven't actually done anything yet, and I would like to do that next. Now, if you read the tutorial, it will walk you through everything that we just did, and then it will start introducing a kind of program that we're going to write. And the program that we're going to write for this is a game of rock, paper, scissors. Now, I know that you don't care about the game of rock, paper, scissors. Nobody really cares about the game of rock, paper, scissors. But when you are learning DApp programming, really when you're learning anything, you're always faced with learning two different kinds of things. You can learn the techniques that you use to do something, and then you can learn the domain that you apply it for. So for instance, suppose that I want to learn how to make a website. Well, I can learn how to use the tools like HTML and CSS and JavaScript. And I can also learn about, for example, writing social networks. And so if I wanted to make a social network, I first have to learn how to write websites, and then I have to learn how to make a social network. And obviously it's very complicated to do both of these things. And sometimes it can be useful to learn the mechanism, the techniques, before you actually apply them. We do something very similar to this in school when we learn things like, you ultimately want to be an engineer that works on cars, but before working on cars, you work on, breadboards that are completely abstracted from any real work, because it can be a simpler domain that is more straightforward to work with. So rock, paper, scissors is our choice for a simple domain, because we don't want to choose a domain where we have to teach people about the domain in addition to teaching them the mechanics of writing Reach programs. So rock, paper, scissors is nice because most people already know what it is. And if you don't know what it is, it's very simple to explain. It's a game where two people are going to choose between one of three options. They're either going to choose between rock, paper, or scissors. And there's a very simple rule, which is that they each choose their hands independently of one another without knowing what the other one does. So like behind their backs, for instance, one will choose rock and one will choose scissors, and then they will reveal them at the same time. And then there's a very simple set of rules that determine who wins. Rock will be suffocated by paper, but will smash scissors, and scissors will cut paper. That describes the complete set of rules of the game. And so if you didn't know what it is, now you do. Well, by focusing on this simple game, we can ignore the details of that and focus on reach. So what I want to do first is show you the most basic version of this game, and then we'll go to the end and look at the most complicated version of it. Okay, so I'm actually going to copy the code from my repository, so I don't have to type it all in. Just going to look at the questions real fast. So someone asks, are there Python SDKs for Teal or Reach? If you're interested in directly using the underlying Algorand virtual machine, which is called Teal, then you can program that completely directly. To do that, you'll want to learn how to write Teal programs, and you want to learn how to use the Algorand SDK. And if you want, there's a tool that's called PyTeal, which is designed to make it easy to produce Teal programs. It's sort of like a convenient syntax for producing the assembly code. So you can kind of think of it as like a macro assembler for Teal. Now, if you want to use Python for Reach, with Reach, then when you write a Reach program, you're writing in this JavaScript-like syntax. However, when you write your test suite, or the program that actually interacts with it, in here, I'm also using JavaScript for that. But this part right here, you can actually use any language you want for that. Right now, we have implementations of this front-end interface for JavaScript, Python, Go, and C#. The C# one is currently experimental, and we haven't pushed it out yet. But if you're really interested in that, we can, get you access to that. Yeah. Okay. So I have just plopped a whole bunch of code on you. And so let me describe what it is a little bit. Although someone does ask a question, I want to be very cognizant of the questions to make sure that, because you can go find a video of me talking about this kind of thing, but the questions are special. So someone asked, does Reach support KMD and Algorand indexer? So Reach uses the Algorand indexer to implement the Reach standard library. But this question is a little bit strange to answer because Reach doesn't support or not support any particular Algorand feature. Instead, the way that we think about it is that Reach provides an interface and a development platform for writing decentralized applications. And Reach defines its own concepts for what you want to do with a decentralized application, and it deploys two particular consensus networks using the features that are available to them. So I think it's going to be more clear about how this relates to the indexer when I talk through this little program. So let me sort of flag that right now. So as I mentioned before, when you define a Reach application, you define the players of the game. Of course, it doesn't have to be a game, but the actors in this computation. In this case, we have one actor called Alice and one actor called Bob. In between these braces, we write down all of the things that each one of that participant can do during the game. And in this game of rock, paper, and scissors, they can return the hand that they want to play, and they can see the outcome of the game. So they have to provide a function that's called getHand that will return a numeric representation of their hand, and they can see the outcome of the game, which we represented as a number as well. After we deploy the program, we're now going to write down all of the steps of the computation. And these steps of the computation will be enforced by the contract that gets generated, and each one of the participants will individually execute it. And since each one will be individually executing it, we have to annotate which things are only done by Alice and which things are only done by Bob. So the way that we're going to write this program is that first, Alice is going to call the getHand function and name the value hand Alice. And then she's going to publish it for all the world to see. Because one of the things that consensus networks do is they allow us to share information with the whole world in a way that can be tied directly to us. So when we write alice.publish, we'll know that if Jay is playing the game as Alice, then Jay is the person who sent this and nobody else did. Nobody else can send it because they are not Alice. And if in the future someone says, what did Jay do during that game of rock, paper, and scissors, 10 years ago, they'll be able to verify that he really did send rock. So it's published forever. Now, one thing that you may notice is that there's this phrase right here, declassify. So one of the things that Reach does for you is it does what's called an information flow security analysis. What that does is it says that we're going to assume that all the values that each participant knows are initially secret and they don't want to share with anybody. And they have to explicitly opt into sharing them by declassifying them. So you can kind of think of this as like, spy networks in movies, where everything they do is by default classified, and they have to explicitly say, declassify this to share it with the world. And when you publish something, you are sharing with the world, you're sharing with everybody. Now, after we publish something, we are now in what Reach calls a consensus step. A consensus step is a part of your computation that everyone in the world agrees on what its inputs are and what its outputs are. So in this case, everyone in the world agrees that the input to this step is hand Alice, and the contents of it are actually nothing, so we immediately commit. Commit inside of Reach says the consensus step is done, and now we're back to a normal step that is not consensual. So next, we're going to have Bob do the same thing, where he's going to get his hand and then declassify it, and then he's going to publish his hand. Now, at this point, we both have, there's a hand for Alice and a hand for Bob, so we can compute the outcome of the game. Now, you might expect to see a table that says something like, oh, well, when Alice is rock and Bob is rock, that means it's a draw. But actually, it turns out that there is a cute modular arithmetic formula that can compute an outcome. And so that's what we do here. And then we commit. And then each one of Alice and Bob gets to see the outcome of the game. So that right there is the Reach program. And now I want to walk through how we write an automated test suite for this program. Now, a lot of the code is the exact same from before. We get the ability to load the standard library, we load the compiled code, we load the standard library, then we set up the test accounts, one for Alice and one for Bob. We have Alice deploy the contract, we have Bob attached to it. And now what we're going to do is we're going to actually implement these functions. Let me actually skip this middle block and show this code down here. We're going to launch the program with Alice playing as Alice, and we'll launch the program with Bob playing as Bob. And each one of them is going to use the player interface. They use the player interface because the Reach program specified that Alice was a player and Bob was also a player. And the player interface says there has to be a getHand function and a seeOutcome function. So player is an object that's parameterized over who that has a getHand function and a seeOutcome function. The getHand function, what it's going to do is it's going to randomly choose a number between 0, 1, and 2, because it's going to randomly choose rock, paper, or scissors. And we're going to print out a message that says, so-and-so played this thing, and then we're going to return that. So notice the flow of information. The front end, that's this test JavaScript program, it is going to start a particular Reach backend. That Reach backend is going to run and eventually call back into the front end, at which point it will do some computation and return a value. When it's totally done, it will call the seeOutcome function, which will write Alice saw the outcome, and then we'll say either Bob wins, draw, or Alice wins. Why 0 means Bob wins has to do with the details of this modular arithmetic formula. All right, let's just run the program so we can see how it works. So we'll run reach run. I keep doing dot, but I meant to do dot dot because I put the file in the previous directory. All right, so we'll do reach run, and it compiles it. It starts up a devnet, and then it runs it. So it says Alice played paper, Bob played rock, Bob saw the outcome Alice wins, and Alice saw the outcome Alice wins, because paper beats rock. Now notice that when I wrote this front end, I did not have to think about details such as, well, which Algorand account am I going to use? How do I make an Algorand application? How do I query the indexer? How do I submit a transaction? Those details are all completely taken care of by the Reach standard library. This is even true when you launch a web application. At the very end, I'm going to talk a little bit about how to use Reach on the web with a wallet as opposed to this automatic command line interface. Now, at this point, it's useful to talk about this question that someone asked: does Reach support KMD in the Algorand indexer? So let's think about how this program has to work. So we can actually skip this part of it, okay? So imagine that we're running this program as Alice. Well, what we're going to do is we're going to say, okay, well, this says Alice only, so that means that I should do this part. I'm going to call the getHand function, and then I'm going to publish it. Well, what does publish mean? Publish means to construct an Algorand transaction, send that transaction to the network. Well, of course, sign it first, send that transaction to the network, and then make sure it gets confirmed. And then any logic that is in between the publish and the commit, that's really code that is actually inside of that contract. If we were to go look at the compiled TL code, we'll see that there's a part of that corresponds to this block right here. Next, remember, we're Alice. We're not going to run this code because it says bob.only. And we're also not going to run this code because it says bob.publish. But when Bob publishes something, that means that we actually want to receive something. We want to listen for it. And so that means that this line right here, when we compile it from the perspective of Alice, actually gets turned into a query of the Algorand network that says, tell me about the time at which this contract was called, and it was called with arguments that mean we're at this part of the program, and tell me about what hand Bob is. And so that publish right there from Alice's perspective is actually a query of the Algorand indexer. It will query the indexer and find this call. And then now, after we've received that, we've read that call, that means that Alice now knows hand Alice and it knows hand Bob. And because it knows those two things, it can actually interpret what the contract did on the real network and figure out what the outcome would have been, because it knows that it has the same values as the other ones, as all the other participants in the network. A consensus network is called a consensus network because it allows many people in a decentralized computation to reach consensus about the outcome of a computation by agreeing on all of the intermediate values. If everyone agrees about what code is going to run, and they agree on what the values that that program uses, then that means that they will agree on the outcome of the program, so they don't need to disagree about what that is. So because of that, Alice can now see the outcome because she knows what hand she submitted, and she knows what hand Bob submitted, and she knows that the outcome that she computes is the same as the outcome that was computed on the network, and so she can see what the outcome is. Let's look at it again from Bob's perspective. Well, Bob isn't going to run Alice only, and when Alice publishes hand Alice, he's going to actually listen and make a query of the indexer for that same information, and then he'll publish, and then he'll have the same stuff. So if we actually run with debugging mode turned on, we could actually see all of these things. This is going to be a lot of output. So, strap in. Okay. So there's a lot going on there. If we scroll around, we can see a few things. So let me actually go up to the first message. Okay. So this right here is when I wrote this compiler, and I wrote the interaction with the network, so I can just read these things and know what's going on. You're not supposed to be able to read this. So for instance, I know that when what this line right here means, wait for confirmation. This right here is Alice confirming that her publish actually worked. She sees that it was confirmed in round 39. She confirmed round 39. So she sees it was confirmed in that round. And then when she sees that it's confirmed, then she goes and checks for that to appear on the indexer. And so does Bob. Bob is also going to look on the indexer. And so he's going to do a search for transactions, which is a query that the indexer has. And we're going to look for things that are to application ID 37, things that are applications, and things where the minimum round is 39, because we know that the round is that the last round that something happened was 39. And then we're going to receive this result where, okay, well, now it's round 38, and this is the transaction. And it's going to know how to decode this application transaction to read off hand Alice. And if we scroll down in the program, we're going to see that Bob is going to do something very similar, where he is going to send off, he's going to send off his thing. But while Bob is publishing this, Alice is going to be looking for it. So for instance, we can see right here that Alice, which happens to be FW6B, she is searching for another thing that starts at around 40, where she's looking for Bob's transaction, but oh, there's nothing there. It's there. The transaction set is empty. So she has to keep waiting. And eventually Bob will succeed publishing it, and then Alice will be able to read it, and then they'll be able to continue running the program. Okay, so that's what I mean by the fact that Reach defines its own abstractions about what you want to do based on the program that you write in Reach. And then we map that to concepts that already exist on the consensus networks that we support. And that, of course, uses features that you've heard of in Algorand, such as ASAs and transactions and applications and the indexer and so on. Okay, now Special K asked the question, is Reach itself decentralized? Reach is not decentralized because Reach is a compiler like GCC or Clang or Node.js. So if I were to say, is, I don't know, the Swift compiler decentralized? I mean, it's possible to imagine a decentralized compiler. Maybe we could like have a service out there where you send it, programs that you want compiled, and you have to pay us 1 algo for every compile or something like that. It's conceivable to make that, but that's not what Reach is. Reach is a program that you run on your computer that compiles a Reach program and turns it into a program that you can deploy on Algorand, on Ethereum, and other consensus networks. And it is also a testing and deployment tool that allows you to run test suites like this. The next question, Oyster Pack says, in this case, get hand is executed off chain and the hand gets published on chain. Correct? Yep, that's exactly right. The code inside of an only block is what we call untrusted, which means that since it's not part of a consensus step, there's no guarantee that the participants actually ran it correctly. I don't know if you've noticed, but every time we compile, it says that we're verifying the program. So it says verifying knowledge assertions, verifying for generic connector, verifying when all participants are honest, verifying when no participants are honest. What's going on right there is that behind the scenes, Reach is going to check a whole bunch of theorems about our program to make sure that we're not violating certain properties that are essential. For example, it should not be the case that our program ends with money locked away in the escrow account, because once it ends, that escrow account is locked forever and there's no way to get the money back. So if you were to transfer funds to it and those funds did not leave by the end of the program, then those would be lost forever. There are, in fact, multiple instances in the history of blockchain networks where contracts have locked away funds forever for exactly this problem. And Reach will automatically check that that does not happen. But when it does this verification, it's not safe for it to trust that Alice really ran this exact code. All we can do is we can check to make sure that Alice published something. And so your code has to be safe regardless of people do things honestly. Now, the thing though is that we check to make sure that we verify in one mode where we assume that everyone did act honestly. And that helps us to establish that honest participants will never try to submit a transaction that is guaranteed to fail. And then we also run a mode that says where no participants are honest. And what this does is it checks to make sure that even if participants are not behaving honestly, they just publish random or attack values, then the quality of the program is not compromised. Okay, now the next question is, how does Alice know which hand that Bob published to use? What if Bob publishes multiple hands? So notice that the program only contains one instance of Bob publish. That means that the application guarantees that Bob can only do this one time. If we were to study the details of the Teal program, one of the things that we would find is that it uses application state to keep track of what line of the program, well, it's not literally what line of the program is, but you can imagine what it does is it checks what line of the program it is. So for instance, when the program is constructed, it says, I'm on line 15. And then it says, well, on line 15, the next thing that I expect to happen is a publish on line 20. So that means that I expect to receive a value from Alice that's her hand. And then after that, now I'm on line 21, which is this commit. And after that, I should be expecting a message from Bob, where Bob is supposed to publish something. And that happens on line 26. And then after that, now I'm on line 29, and the program's actually over. So now I deallocate. So it's not possible for like Bob to publish multiple times, but it would be possible, for instance, for like because the program's over. But imagine you ask the question, well, what if Alice publishes multiple times? Well, Alice publishing multiple times means Alice tries to run the program at step 20 multiple times. But after we run at step 20, the contract says, oh, I can only run the program that's on line 26. And so that means that you can't do step 20 multiple times. Of course, the language supports while loops and stuff like that. So it's not like it's not that things literally can only happen once. But in this particular case, that's why we know that that doesn't happen. Someone asked the question, are there any Reach grants open? So Reach runs two things that you may be interested in. One is that we run many bounty hacks, which are like hackathons, where people are basically assigned interesting programs to test their ability to make things with Reach and on Algorand. And those have participation prizes and prizes for the winners. Also, Reach is part of the Algo Scout project, which is for giving basically initiation grants for people building interesting things on Algorand. If you're interested in either of those two things, I suggest joining our Discord to learn about them. Our Discord, by the way, if you go to the homepage of the documentation, there's a big link that's here. It says, start a discussion on the Discord community. You can check it out there. Okay, so we ran this simple program. Now, this simple program is not good. And one of the main reasons it's not good is because Alice publishes first and then Bob publishes, that means that Bob can actually like look at what Alice did and choose the value that would make him win. So for instance, we can just change this program right here so that rather than asking for the hand, where we're going to say the hand Bob is equal to hand Alice +1, I think. We'll make it so he wins all the time. So if we do Reach run, we will see that he will either win all the time or lose all the time. So yeah, so Bob won when Alice played scissors. And notice that the front end isn't even called because we removed the interact get hand. And the reason that this happens is because when Alice published this, she published it to the entire world. Everyone knows what it is, including Bob. So he can use it to choose a better, the value that's going to make him win. So this is an example of a bad program. Now, Reach has all sorts of things to help you not write bad programs. So what I'm going to do is I'm going to skip forward to kind of near the end of the tutorial and walk through some of the changes that we made to the program. First thing I want to do is show the front end actually, because the front end actually is exactly the same as it was before. So the front end works the same, except that we also show how much money each person gets, and we make it so that there's actually a wager involved in the game. So I'll comment on those things in a moment. But let's go up and look at the program. Okay, so the program is a bit longer because we're going to use a few abstractions to write this program. So right here we have make enum, which makes an enumeration of values. So we're going to have one for rock, paper, scissors, another one for B wins, draw, and A wins. This is just to make it so our program is a little bit simpler. We're going to abstract away the winner function, and we're going to write some test cases that says, rock and paper should result in B wins, paper and rock should result in A wins, and rock should result in a draw. And so these are test cases like you would expect to find in any programming language. But Reach has a special way to write test cases where you can write a for all theorem. And so this says for all numbers hand A and for all numbers hand B, the winner of hand A and B is one of these valid outcomes up here. We can also write the assertion that for all numbers hand, when you play that hand against itself, it's a draw. And so these test cases will be checked when we run the program. We've also expanded the player interface so that there is a way to get random numbers. And there's a way to observe that a timeout has happened. One of the things that happens a lot in dApp design is you have to deal with the possibility that one of the players ceases participating and just doesn't do anything anymore. And you have to be resilient to this happening in your program. We're also going to expand the interfaces so that Alice is going to propose a wager in algos, really in microalgos, and she's going to have a deadline by which Bob needs to respond by, or else the game is off. And Bob can selectively decide whether he wants to accept or reject this wager, because maybe he doesn't want to play, rock, paper, scissors for 10,000 algos. All right, we define a little helper function to let us know when there's a timeout, and we're going to declassify the wager. We're going to have Alice compute her hand. Then what we're going to do is we're going to make a cryptographic commitment to the hand. This is a design pattern that you see a lot in dApp programming, where rather than sending a value, you send a hashed version of that value. This means that Alice cannot go back and change her mind about what her hand is, but Bob also cannot see it. Then what she's going to do is she's going to publish her wager, what she commits, and the deadline by which Bob has to respond by, and she's going to pay into the contract the amount of the wager. So she's going to transfer to the contract some funds. Now, if you know anything about Algorand, you know that applications cannot receive funds because applications are not accounts. This is a good example of how Reach defines its own abstractions and then compiles those as best it can to the underlying network. So when you create a Reach application, when you deploy a Reach application on Algorand, you don't just create a Algorand application, you also create an extra escrow contract that is tied to that application. And so that's the place where these funds go. And so if we were to look inside of the Teal program for this, one of the things that it's going to do is it's going to make sure that this value that was sent matches the amount of funds that got sent to the escrow contract. And that's going to be inside of an atomic transaction group that is enforced by all the different parts of Teal. The next thing that we're going to do is we're going to make a knowledge claim. So this knowledge claim says that Bob cannot know what Alice knows about Alice's hand or Alice's salt. One of the things that Reach allows you to do is write these verification claims about who knows what, so you can make sure that you don't have errors in your program. Before, if we tried to include this theorem, it would have been false because Bob would actually know the hand of Alice at this point. Then Bob can decide whether he wants to accept the wager. And if he does, he can get his hand, publish it, pay the wager. And if he doesn't, let us know that Alice, let everyone know that there's a timeout. And then once he does that, we can now have Alice reveal her hand and her salt. We can check to make sure that they match so that she can't, for instance, look at what Bob did and respond to that. And then we can change the outcome. We can compute the outcome. And then we can compute that if A won, then 2 units of wager will go to Alice, otherwise 0 will go to Bob. If Bob won, it will be the reverse. And if there's a tie, then they each get 1. And we'll transfer some to Alice and some to Bob, and then we'll be done. So if we look at the program, we see that most of it is the same. Get hand is still chosen randomly. We see a little message for observing a timeout. And then Alice is going to propose a wager of 5 algo and a deadline of 10 blocks. And Bob will accept everything. But sometimes when he's asked to accept, he's going to flip a coin, and 50% of the time, he's going to delay for 10 blocks before responding, which will result in a timeout. So if we go run the program, we will see very similar output from before. Notice that there were 57 theorems proved rather than just 10. Oh, it looks like Bob is timing out. So Alice played scissors. Alice observed a timeout. Bob tried to play scissors, but he failed and observed a timeout. Alice went from 10 to 9.992. The reason that that's slightly lower is because she had to pay to deploy the contract, and she had to pay a fee to send her first message and to claim her funds. And then Bob didn't spend any money. If we run the program again, maybe this time Bob will decide to actually play. We'll find out because it's chosen randomly. So, all right. So Alice played scissors. Bob accepted the wager of 15. Bob played rock. Alice saw that Bob won. Bob saw that Bob won. And Alice went from having 10 algos to having 4.92. And Bob went from having 10 to 14.998, just like we expect. All right. So now from here, the tutorial gets a little bit more complicated. We were just looking at tutorial 2.6. The thing that happens next is that we make it so that the program will continue running until we do not have a draw. So let me just run the program. Whoops. Yeah. So let me run again. You can see it going. And we'll just, that now the code is exactly the same, although I made it so that Bob will never time out. Oh, sorry, he'll time out like 1% of the time rather than 50% of the time. So here there was no draw, so it behaves the same as before. It only behaves differently when there's a draw. Yep, okay, so there was a draw. Oh, wow, 2 draws in a row. There we go. So notice that they pay slightly more in fees because they had to do more interactions. This program looks very similar, except that there is a while loop, and this while loop just says that while the outcome is a draw, keep playing the game. So this is what it looks like to write a simple reach program. What you do is you define your domain that you care about, and you make sure that you have a good understanding of it. You define the interfaces that the participants in your DApp will perform. And then you write out meticulously all the steps of the program, who can do what, in what order they can do it. And as you're doing that, you can, transact funds as you go. Someone asked the question, how does one restrict or control gas or transaction fees when using Reach? So I don't know exactly what you mean by restricting or controlling them. You can't really decide how many transaction fees or what gas you'll pay when you use a consensus network. You kind of have to take what is given to you. So Reach has a pretty sophisticated optimizer to try to optimize your program to make it so that it will use as small programs as possible, because bigger programs cost more in Algorand. Not luckily in Algorand, all programs cost the same to run no matter what, but there's a very small limit. It's sort of the equivalent of there being like 700 gas. It's not exactly that, because some computations, because gas doesn't really mean the same thing on Algorand. But yeah, so that you kind of have to take what's given to you. But this is an automated program. And so because this automated program has a test account, like what is a test account? Well, of course, any of us can make accounts for Algorand whenever we feel like it, because they're just random public-private key pairs. So what new test account does is it makes a totally fresh account, and then it sends money to it from the faucet. And so since it is a totally new thing, we actually already have the private key. And so it is configured to just sign every transaction. In contrast, if we wanted to build this for the web, we wouldn't write that. We would write, account Alice equals await standard library. I think it's called get default account. And what that's going to do is it's going to query your wallet and say, give me access to this account. Well, now that we're asking your wallet, it's now your wallet's job to sign and approve every transaction. And in that case, the individual end user is going to be able to, see this transaction costs this much, and they're going to have to decide whether or not they want to do it. And if they don't do it, or they don't do it fast enough, then the program will time out. It would be nice, I think, to develop Algorand wallets that have some sort of ability to say something like, you have access to one algo, sign everything that costs less than one algo so that I don't have to, have this UI dialogue a lot. So I think that might be the question that you're asking, about how to control the fees. Yeah. So that's kind of the structure of writing a Reach application. I'm going to talk a little bit now about some of the stuff in the tutorial that I didn't talk about. We go into quite a bit of detail about how the theorems work, how the timeout stuff works, how to design the while loops. I think that you should read the tutorial and work through it. 2.8 walks through building a command line interface for this program that can use a real Algorand network. So for instance, let me kind of skip very to the bottom. You will get an interface that's like, are you being Alice? Do you want to create an account? Do you want to deploy the contract? How much do you want to wager? And this right here can run and has run many, many times on the real actual Algorand networks. So if you wanted to, you could build a user interface like this. That's not a very exciting user interface. So you probably want to build one that uses the web. And that's what 2.9 is about. So 2.9 is about building a React program that uses Reach. And the most important thing about this is that this program is exactly the same as the command line one, except that all the code that does command line stuff is replaced with doing web stuff. The reason that's important is that Reach does not need to know how you are going to write your front end. You can write your front end so it's an automated test suite. You can write your front end so it's a command line interface, or you can write your front end so that it's a web program. Reach doesn't care. There's no different about it. And so there are some screenshots about what the program looks like and how it works. And really this, if you read this, it's essentially a tutorial about how to use React and how to just do the very tiny connections that make it work with Reach, which isn't very much. Now, once you're there, obviously there's a ton more that goes into writing dApps, because probably you don't want to write a rock paper scissors program. You have some other program that you're interested in building. And at this point, there's the Discord community that can help you learn about Reach. There's the workshops, which give you some ideas about programs to write and how to do them. Some of these programs have links to some Reach programs that do it. So for instance, like imagine that you want to make an NFT where you auction off the NFT and then give a portion of the funds to whoever, whenever it gets sold, a portion of the funds go back to the creator. Well, you can look at the examples NFT auction program, and it is that program. So this is an 85-line program that manages an NFT and makes it so that every time someone wants to sell it, they auction it off. And after they auction it off, a percentage of the funds go to the creator. And there's a very simple test suite for it. And this test suite is run, hundreds of times a month on Algorand and all the networks that we support. You could also go investigate the reference, where there's an excruciating amount of information about all the different things that you might want to do and exactly how Reach works, all the features that aren't otherwise talked about. So for instance, one of the things that Reach can do is you can, mint a new token. And when you mint a token, that of course means an ASA on Algorand. And so you can mint a token and deal with it. You can also use, application local state. These are called mappings on Reach. So they can store information associated with all of your users. So for instance, like maybe you want to do, I don't know, like a raffle or something like that, where you keep track of all the people who have bought a raffle ticket. So, the sky is quite the limit when it comes to writing Reach programs. But if you want to do this, what you should start with is read the overview to get a taste of what Reach is about, and then go through the tutorial and, actually write every line of code yourself so you can get a feel for what it's like writing Reach programs. I'm, of course, very willing to answer any questions that you have. And this is kind of the end of the presentation. We're about an hour in.
Fantastic. Thank you very much, Jay. That was great. Yeah, and if anyone has any kind of last final questions, feel free to pop them in the chat now. But yeah, I think we've had some great questions throughout, and thank you very much for handling those. Just on the kind of Algorand Hackathon side, obviously we have one final workshop, which is the ideation workshop, taking place on Wednesday, exact same time. So make sure to come along to that. And all the previous workshops are available on our website and our YouTube, and are in the Discord as well. So yeah, check those out if you need to. And this will be uploaded tomorrow as well. So if you wanted to go over something, or then you can check that out there. But yeah, apart from that, I'm just going to pop the link to the challenges article, as we released that last week as well, which kind of gives a bit more information on the challenges and that as well. But yeah, we've got a couple more questions come in, Jay.
Yeah, I've been following them.
Sure.
Yeah, so let me answer the questions. So one person asked the question, are there any ETH algo bridges? So Algorand has this feature that's called a compact certificate that is designed to make it easy to create such bridges, but there's not any commonly deployed bridge or bridge creating system with Algorand. That's something that a lot of people in the Algorand community are really interested in building, and we at Reach have some ideas how to do that. I'm answering this question first because it's kind of the easiest one to answer. The next, someone else says, what's the smartest way to build a copy of a DeFi protocol like Aave? So imagine that we wanted to make a copy of Uniswap. So I'm just going to go to the Uniswap contract for a pool. And so this right here is the code for implementing a Uniswap pool in V3. So it's, 800 lines of code. There's lots of complicated and interesting details. And it, of course, requires a whole bunch of libraries to get started. Even if we were to go back to version 2, which is considerably simpler, it's not called that, Uniswap 2 contracts and pair. Okay, so this program is simple, is much shorter, so it's only 200 lines of code, and it does have some complicated libraries. But imagine that we wanted to implement Uniswap on Algorand. So there are many details that are inside of this program that I think are very difficult to imagine how to translate this program to Algorand. Just as a tiny example, notice that it uses events, which are an abstraction inside of Ethereum, and it emits these events. So like here's an emission of an event when there's an update. So Algorand doesn't have a corresponding concept. So one of the things that you need to do if you were to adapt to this program is you'd have to adapt each idea as you go. And I just think in general, when you are converting from one thing to something else, it's often better to kind of take a first principles approach and say, well, what is this program supposed to do? And from what it's supposed to do, design a corresponding program. So if we look at Uniswap, and we can go, I like Uniswap because I know that they have this really beautiful picture that I'm looking at for you. Where's this picture? Maybe we can go to V2. There's this cool picture that I like, how Uniswap works. Ah, yes, this picture. Okay. So it's a little bit small, but let me open a new tab. So this picture right here, it essentially describes everything you need to know about what Uniswap is, combined with this picture right here. And Uniswap is extremely, the developers of it and the people explaining it are just extremely wise and be able to make these amazing graphics to explain what's going on. So from these two pictures, you're going to learn way more about what the point of Uniswap is and how it works than studying this program. This program is going to be focused on all of the low-level implementation details about how to realize this business logic. And as you're designing your dApps, I encourage you to focus almost entirely on the business logic and then look for an appropriate tool that allows you to express that business logic clearly. So one of the things that we've done, for instance, is we've written a version of Uniswap in Reach, and it is quite succinct and simple. And we did it by designing something with the same feature set based on the design of Uniswap, as opposed to actually translating the program. And I encourage you to do that as you kind of approach stuff like this. Someone asked the question, apologies if I missed this, but how does application updating work in Algorand? Is it possible to update the logic after it's deployed? Is there also a way to block updates? And then they have the follow-up updating in Reach, sorry. So I think that from this question, you know that on Algorand, it is possible to update applications because there is a transaction that you can format that's called update application that allows you to add new code to an application. If you've written a dApp that uses stateless contracts, however, they can't be updated if you're using them if you're using the contract signature as the account. But if you're using the contract, if you've given the contract signatory access, then not only can you you can update it, but you can't prevent the older version from having access to your account. So anyways, so within the kind of that framework, yes, on Algorand, it is possible to update applications, and we do not support this at Reach because we think that it is important for people to be able to rely on your program obeying the invariants that are expressed in it. So for instance, we want to make sure that when you're running this program, no one can change the rules of the program at some later point. Now, of course, updating applications is a bit of a tough thing, right? Because if you allow them to be updated, then essentially what you're doing is you're making it so that a centralized authority can change the rules for everybody, potentially disadvantaging people who are already using it happily. And so that's kind of the negative story for applications. The positive story for applications says that, sorry, for updates, the positive story for updates says that, well, I can write something, and if I discover a problem, then I can change the program. And that sounds like a good thing. But it's crucial to have your users understand these two different sides, because maybe the reason I want to update it is that I've hoodwinked enough people that now the contract controls 10 million algo, and I would like to switch the rules so that the only way to get it out is for it to be sent to Jay. So updating applications is extremely dangerous and is not something that is turned on in Reach. Other applications can do it. And of course, on the way that we can turn it off is that we just make it so that Reach guarantees that no transaction that attempts to update your application will ever succeed. So it's not that you can't literally turn it off on Algorand, but you can deny and promise to deny all attempts to update, which is what we do. In the future, we're interested in doing something for updating to allow that as a feature, but I think that you should not trust things that update unless they are backed by, for example, a very reliable DAO. So for if a contract controls access to a large pool of resources, then those resources should basically be a priori claimed by participants, and those participants should be able to decide on updating the application, for instance, in proportion to what their ownership is. That's a pretty typical strategy that people use for updating now on networks like Ethereum. But of course, updating on Ethereum, you can't literally update the application. You can transfer to a new one. And Algorand essentially makes it so that you don't need to transfer. You can change the rules as you're going. All right, any final questions?
I think that might be all of them. So yeah, thank you very much again, Jay. I had a lot of thank yous in the chat, and again, a great presentation. You can check out Jay's previous one also on the website, but this was very fantastic. And yeah, thanks a lot. we will.
And
Yeah.
I hope to see you all on the Reach Discord, and I hope to see all the exciting things that you build with Algorand. Algorand really is one of the coolest networks that are out there. It's so fast, it's so cheap, and they have a really responsive developer community, and we're very grateful to be a part of it. And we're grateful for all of you being part of this hackathon.
Awesome. Well, yeah, thanks again, Jay, and thanks everyone for attending. This will be uploaded tomorrow, but have a great day wherever you are, and see you all soon.